Any aircraft flying into modern contested airspace enters a dense web of integrated air defense systems. Missile platforms like the S-400 and India's developing Project Kusha project a highly lethal kill zone capable of tracking targets up to 400 kilometers away. A traditional fourth-generation fighter jet like the S-30 Mk3 presents a massive 4-square-meter radar cross-section to these networks. It lights up enemy screens miles before it gets close enough to deploy its own weapons. Because an aircraft cannot physically outrun a Mach 5 interceptor missile, it has to hide. This strict tactical reality drives the design of fifth-generation stealth initiatives like the AMCA and the autonomous Ghatak drone. To guarantee a vital first strike advantage, aerospace engineers have to take a 25-ton machine and shrink its physical signature down to almost nothing. This diagram illustrates radar cross-section, or RCS, the true physical measure of an aircraft's visibility. It contrasts a standard fighter's 4-square-meter reflection against a microscopic footprint of 0.0015 square meters. That smaller baseline reflection is roughly the size of a small bird. To achieve that, engineers shape the hull to physically deflect incoming waves. Tilted twin tails and aligned platform edges bounce radar energy away from the enemy receiver. Removing the tail entirely to create a flying wing geometry pushes that reflection profile even lower. The hull is then coated in radar-absorbent materials, which soak up and attenuate over 99% of any remaining electromagnetic energy. Constructing up to 40 radar evasion dictates the shape, material composition, and loadout from the very first blueprint. But radar is only one threat. Surface-to-air missiles also hunt using infrared sensors locked onto the intense heat of a jet engine. This thermal visualization compares the massive heat plume of a traditional afterburner against a suppressed stealth exhaust. By utilizing non-afterburning engines, like the developing GTRE dry Kaveri, combined with heavily shielded exhausts, engineers can mask the aircraft's infrared output. Deep inside the engine, fast-spinning compressor blades generate extreme acoustic noise and act as highly reflective targets for incoming radar waves. This cross-section shows how diverterless supersonic inlets and S-shaped serpentine ducts physically block outside sensors from having a direct line of sight to those spinning blades. Hiding the heat and sound requires engineers to completely redesign the physical mechanics of propulsion. The result of these modifications is a 25-ton machine operating as a completely undetected sensor amplifier, capable of executing devastating first strikes. However, ground-based radar networks are actively evolving to track these low observable targets. New tracking systems, like India's Virupaksha active electronically scanned array, operate as 4-dimensional radars, simultaneously calculating a target's range, azimuth, elevation, and relative velocity. This solid-state array, built with gallium nitride modules, handles immense thermal energy to generate overwhelming processing power. This power is deployed to mathematically filter out massive background noise, isolating and tracking the faint bird-sized returns of stealth aircraft. As air defense radars evolve to burn through the interference, aerospace engineers must shrink aircraft signatures even further in an endless high-speed war of physics.